Semiconductors are the invisible infrastructure of the modern world. Every piece of digital technology you interact with, from the phone in your pocket to the satellite routing your GPS, relies on these microscopic switches to function. They also drive major national milestones. When India's Chandrayaan-3 safely touched down on the lunar surface, launched the first India Semiconductor Mission in 2021. That initial push successfully convinced global tech companies like Micron to break ground on domestic soil. This graphic maps out the mission's footprint. As of December 2025, 10 strategic manufacturing projects were approved across 6 states, with multi-billion-dollar investments landing in places like Gujarat and Odisha. But there was a catch. Even with new factories pouring foundations, the ecosystem had a structural vulnerability. The intellectual property inside the chips and the highly specialized machinery required to build them were still largely imported. Running an assembly line creates jobs and localizes the final product, but if another country owns the blueprints and the manufacturing equipment, true technological sovereignty remains out of reach. That specific gap is what the new 1.27 lakh crore, or roughly $15 billion, Semicon 2.0 initiative is designed to close. Instead of simply packaging silicon produced elsewhere, this second phase pushes the industry upward into the creation of indigenous chip designs, raw materials, and the complex machinery needed to make them. The policy breaks this challenge down into a 6-pillar architecture. It supports design creation, raw materials and machinery, expanding silicon fabs, advanced packaging, next-generation research and development, and talent creation. By treating these 6 areas as interconnected pieces, the mission shifts from a financial subsidy into a comprehensive blueprint for an entirely self-sufficient tech supply chain. The first pillar addresses the brains of the operation, intellectual property. If you print a chip based on someone else's schematic, the majority of the profit and the strategic control over the technology stays with the original designer. This report outlines the design-linked incentive scheme. By co-investing equity alongside private investors, the government is helping startups attract millions in venture capital funding and providing them access to millions of hours of high-end electronic design tools. While startups focus on commercial design, the research and development pillar looks further down the timeline, targeting advanced 2-nanometer and 3-nanometer process nodes. India's initial fabrication projects are currently scaling up to produce 28-nanometer chips, which are essential for automotive and power electronics. Shrinking that architecture down to 2-nanometer gates allows billions more transistors to fit into the exact same physical space, multiplying computing power exponentially. Mastering these microscopic tolerances positions the industry to claim a stake in the future hardware that will run the next generation of artificial intelligence. But brilliant designs are useless without the physical materials to print them. Modern chip fabrication requires ultra-pure gases, specialized photomasks, and precisely engineered chemicals, supplies India has historically had to import to maintain its cleanrooms. This document outlines the specific schemes under the mission. Pillar 2 steps in here with targeted fiscal support to domesticate the production of these exact materials and equipment, stopping the bleed of capital to foreign suppliers. With material secured locally, Pillar 3 aims to rapidly scale up physical output by offering to cover 40% of the capital expenditure for any newly approved silicon fabrication plants. Once the raw silicon is printed, Pillar 4 focuses on advanced packaging. This is the highly complex final step, where the delicate silicon wafer is sliced, sealed, and wired into the gold-plated pin architecture that connects it to a motherboard. By localizing every step, from the raw chemical inputs to the final packaging, India insulates its factories against global maritime disruptions, trade disputes, and geopolitical shocks. Yet all of this new infrastructure faces a massive human bottleneck. Expanding the industry at this scale requires nearly 300,000 new semiconductor professionals, and right now there is a severe shortage of workers with specialized cleanroom experience. To solve this, the talent pillar is actively pushing hands-on fabrication and chip design training down into college engineering programs, getting students accustomed to strict cleanroom standards before they even graduate. Factories eventually age, and manufacturing equipment becomes obsolete, but a highly trained, adaptable engineering workforce is a self-renewing resource that can sustain this ecosystem for decades. This comprehensive strategy is creating diplomatic leverage. India has secured strategic partnerships with the United States, Japan, and Germany. These pacts establish joint collaboration for supply chain resilience, shared research and development, and secure access to critical minerals for defense and clean energy systems. This chart projects the trajectory of the domestic semiconductor market. Driven by this new policy framework, the industry is expected to nearly triple from its 2023 baseline, reaching up to $110 billion by the end of the decade. By meticulously reinforcing the raw materials, the machinery, the talent, and the intellectual property all at once, India is proving that true technological sovereignty cannot be bought off a shelf. It has to be built from the ground up.